So good morning, everyone. Welcome to the Toronto Geometry Colloquium Season 2. This is a weekly web series all about geometry processing.
This colloquium aims at promoting young researchers and researchers from traditionally underrepresented communities. Every week, we will have an opener talking about their cutting-edge research for 10 minutes, followed by a headliner giving us a keynote presentation.
As always, if you have any questions, please feel free to leave comments on YouTube live chat or join our Discord channel to get involved in the discussion or follow up your questions with the speakers afterwards. And today, I'm very thrilled to introduce our opener, José Ezequiel Soto Sánchez. Ezequiel comes from Brazil. He has a PhD in mathematics from IMPA at Visgraph Lab in Rio de Janeiro, which is a beautiful seaside city in Brazil. He is currently a postdoc research fellow at TechGraph, working on geometric modeling and processing. His main research interest is in patterns, tilings, and tessellations. He also has a broad interest in image processing, digital fabrication, data science, machine learning, mathematical visual arts, and computational music. And today, he's going to share a simple integer representation for periodic tilings of the plane by regular polygons using complex numbers. Let's welcome Ezequiel.
Thank you very much, Iris, for the kind presentation, and thank you. I think the whole committee. I've been following the colloquium, and it's an honor to be here, presenting, sharing my work. And so let's get to it. So I'm going to present today an integral representation for periodic tilings of the plane by regular polygons. And I want to acknowledge my co-authors, Luis Enrique de Figueiredo, my advisor in the PhD, Asla, my co-advisor, Asla Medeiros, and Tim White is collaborating with us from UCL. And so the work I'm sharing with you is a recently published paper in Computer and Graphics. Just this year it was published. And so this work is about tilings and patterns, and they are present in nature. And it has been a recurring interest in science and history. And the first one to try to formalize this idea was Kepler, roughly 400 years ago. And he started studying such patterns with regular polygons. So this is a very rigid problem. Trying to tile the plane with regular polygons imposes a lot of rigidity. In fact, one can write an equation around a vertex to look for the configurations. And this equation gives you 15 geometric solutions, although it has more numeric solutions. And these 15 solutions, only 11 of them tile the plane like by one uniform tilings. This is when only one type of vertex is used. However, the rigidity of these solutions, a lot of interesting variety of tilings emerges when you can let the tiling combine the different vertices from the solution. So there are a lot of interesting tilings, and they can grow like very large patterns still in a periodic way. So we want to represent this kind of objects. And how will we do that? So our philosophy is to look only to the vertices of the tiling. And this is how we're going to treat it. And the advantage of working with periodic patterns is that they have translational equivalence. So we can look at the grid, and this equivalence will, the plane modulo this grid will become a flat torus. So we're looking only at the fundamental region at the parallelogram that is indicated there with that topology. And so we can reduce the problem to this fundamental region where we are going to identify the vertices that fall inside of it. After that, the topological reconstruction, this generates an interlocking system of points in the idea of Hilbert and Cohn-Vossen that covers the plane with a set of cosets. And the idea is to reconstruct the topological features of the tiling afterwards. Like the edges and the faces to have the full topological representation of the pattern. So to do this, we're going to give the geometric points lattice coordinates. How are we going to do this? So we're going to put one of the vertices at the origin and to align one of the edges with the horizontal line. This way, all the edges of the tiling will be aligned with a few basic directions. These are the roots of the 12th root of the unity in complex numbers. So all the edges of the tiling are some multiple of omega, the 12th root of the unity in complex numbers. This way, all the vertices in the tiling by regular polygons can be represented by a polynomial in omega, and also the translation vectors. So vertices and translation vectors are expressed as polynomials in omega, but this representation is not unique. However, if we take the modulo over the 12th cyclotomic polynomial, we will obtain a unique representation in complex in integers polynomials of omega of at most degree 3. These are the coordinates of the other powers of omega, so we can reduce everything to 4 integer coordinates. And this way we can represent the tilings with lattice coordinates by only taking into account the 2 translation vectors that define the fundamental region and the set of seeds that are the vertices inside this fundamental region. All of this is written in integer lattice coordinates. This way we have a tiling symbol, which is has this structure where the 2 first rows are the translation vectors that define the fundamental region, and the rest are the n vertices inside the region. Another example of the symbol and one simple tiling. And how are we going to do the reconstruction of the topological features of the mesh? So we're going to take our seeds and our fundamental region, and we are going to generate a vertex cloud just around with 1 copy around each of the possible positions around the fundamental region. And we are going to create a hash table with the integer lattice coordinates. This way, reconstructing edges reduces to a query in the hash table to check the 12 directions and see which are the vertices that are neighboring this vertex. And so we can create the edges around the seeds. And this way we will have a skeleton. This is like a unique copy of each edge inside the fundamental region that can be propagated to hold the plane. And also we can use a procedural method to generate the faces around each vertex. So we will have unique faces that we call a patch. And this patch also covers the plane following the translational grid. Another topological primitive that we can find with the lattice coordinates is the dual, which will be expressed in rational lattice coordinates. And these are very interesting tilings by themselves. So this is why we are interested in them. And when working with patterns, symmetry analysis is very important. As we know, there are exactly 17 plane symmetry groups, known also as wallpaper groups. And we would like to identify the symmetry of each tiling, because this allows their classification as n uniform when they have exactly n-transitively equivalent classes of vertices on their symmetries. And these vertices belong to k Archimedean classes of the ones that I showed you, the solutions. So we have 2 examples here, one 6 uniform 4 Archimedean, another one 5 uniform 3 Archimedean. And the classification of the symmetry groups is very well known. There's a flow chart designed by Washburn and Crow. And this flow chart can be followed exactly because all the symmetry operations in lattice coordinates are going to be exact. And so we can check symmetries precisely with our lattice coordinates. And so we have some examples of the symmetry groups of some of the tilings and the annotated symmetries, which are found automatically by the algorithm, and also the crystallographic regions with the fundamental crystallographic seeds, and a chemical-like notation for each tiling, which will be very useful to identify the class of the tiling. So we have some more examples. And to finish, I will summarize what is in the paper. So we have a compact and efficient representation for very large and complex objects, which is comprehensive. We can represent the whole domain of tilings with regular polygons, except one, that is the tiling with octagons, but it's only one tiling in an infinite family. Its validity is easily verified via topological reconstruction. The symbol is unambiguous. It's very easy to recreate a tiling given each symbol. And we have an abstract uniqueness, which has minor practical challenges of the combinatorial choice of the origin, for example, or the alignment of the tiling. But this can be sorted out with the algorithm. And it is very robust, identifying equivalence between symbols. So we can test whether two tilings are the same. It's a concise representation. It is easy to create given an object. We have made another paper in acquisition. And it is efficient in the context of applications. It's very fast to render tilings with this technique. So this is what we have. We have the symbol, and we can create any tiling with regular polygons. So thank you very much for the TGC, and I leave you the links to the project page and to my personal page. Thank you very much.
Thank you, Ezequiel, for the great talk. This is a very interesting way to generate like the periodic tilings. And as what we usually do, we will move on to our highlighter and have a joint Q&A session in the end. So today, it is my great honor to introduce Professor Alla Sheffer. If you have ever worked in the related field, there is probably no chance that you don't hear of her work before. For example, personally, I learned about her work in the first class of Alex Geometry Processing course, where we talked about her well-known angle-based flattening algorithm for mesh parameterization. So as a quick recap, Professor Sheffer mainly investigates algorithms for shape modeling and analysis in the context of computer graphics applications and have made major contributions to the state-of-the-art research in mesh parameterization, hexahedral meshing, and perception-driven shape modeling. She joined the CS department at UBC in 2003 and have co-authored over 100 peer-reviewed publications, including 42 SIGGRAPH papers, the most competitive graphics venue, and 22 of them were published in the last 5 years. And recently, Professor Sheffer has become a member of the SIGGRAPH Academy 2020 and also elected as a fellow of IEEE and the fellow of the Royal Society of Canada. As a researcher who is probably 5 generations younger than her, the only thing I can say is that this is truly amazing. And if you went to the SGP last year, you probably remember the keynote talk that Professor Sheffer gave about human-centered geometry processing. But today at Toronto Geometry Colloquium, Professor Sheffer is going to share some of her insights about graph partitioning and their applications in geometry processing. So let's welcome Professor Sheffer.
Thank you, Eris. I didn't think I was that old, but yes, I'm going to talk about something very different today than in my SGP talk, because I realized there might be some people who had been to both. And I wanted to kind of focus this talk on some different structure than my usual ones. Usually, I think a lot of talks in geometry processing and in other areas are centered around problems. And what I wanted to center my talk about today is about solution mechanisms, and in particularly about solution patterns, which I find myself using over and over, and which I find are very interesting and worth thinking about in the context of different geometry problems. And we have a lot of such solution patterns in our work, some which are kind of in the continuous space, as things like least squares methods or iterated related least squares, our friends, the Laplacians. And in the case of this talk, I wanted to talk about something slightly different, and that's about discrete methods, which we keep using in our research, and in particular, graph partition. What is graph partition? Well, the idea is you have a whole bunch of entities, be it triangles, tetrahedra, or other entities you operate on, and you want to group them into clusters which minimize some discrete energy function, where this function usually contains weights based on pairings, either pairings of entities where we have a weight or a cost for placing two entities either in the same cluster or in different clusters, as well as pairing weights which are based on associating entities with labels. These problems are in general NP-hard. However, there are efficient approximation methods for some of their variants. And I found myself using a lot of those methods and those particular variants in my work, and I wanted to talk a bit about those. And what's interesting is this type of methods are used in my work and in others for very, very different problems. So let's look at those problems and see some similarities and also maybe some observations about what kind of partitions we typically want. And the first example I wanted to start with is multi-material fabrication. In multi-material fabrication, what we are looking for is we as users want to create an object which has, let's say, different colors on the surface or different surface materials. However, we cannot fabricate such objects using current tools as a single piece. We need to somehow fabricate them in different parts. So the general approach for something like this would be, we have an input model, which we have for the different materials or colors specified on the surface. What we would like to do is to partition it into pieces, each of which has this material, and then fabricate those pieces and assemble them. Notice that this immediately raises the constraints we will need to satisfy. Our parts need to be assemblable, and when assembled together, they need to exactly reproduce the geometry we seek for. Notably, from a user perspective, it's easy for users to provide the segmentation. It is much harder for the users to manually generate the parts. In our experience, even experienced designers took hours to create parts for a given surface segmentation. So our goal from an algorithmic perspective is to start from a surface segmentation and to algorithmically generate those volumetric parts. What kind of parts do we want? Well, they need to conform to the input surface. So once we have that surface, our parts need to exactly match its geometry and be aligned perfectly with the different materials. Our parts need to be assemblable. If we have a 2D case like that, well, those parts are not very useful. If we fabricate them separately, we cannot put them together. In particular, we are looking at linear motion, namely the ability to just move the parts in or out along straight lines. We want the number of parts to be minimal. If we have 2 materials, we would like to have 2 parts. Increasing the part count increases fabrication time and complicates assembly. So we're looking for something like this. This would be our ideal scenario for this input. In particular, we also want to avoid forming really tiny parts because that's problematic from a fabrication and assembly perspective. So what does it mean to compute a partition? Well, if you think about it, this requires 2 things. We need to specify or compute the interior surfaces of every part. We refer to those as interfaces. And we need to, because it's part of our solution, is to be able to make sure that the parts are assemblable. We need to compute the assembly directions. So along each direction, which part can be moved in or out of our assembly. So let's look a little bit more in details as to what does assemblability require. So a part which is assemblable means you can move it along a straight line. You can immediately see in this scenario, this part is assemblable while those 2 are not. But the reasons they're not assemblable are very different. And we separate those reasons into what we call segment extractability. And that's the idea that you can, if you look at the surface of your part or the segment, you can move that segment out. You can see that this is the case for this segment, right? You can see how you can move it outside. This segment, however, will not be extractable no matter how the interface is shaped. So this assemblability part or the segment extractability depends only on the surface. In contrast, if you look at the interfaces, well, this part interface is kind of okay, but this part interface is clearly not extractable. The reason is that we have points on this interface whose normal is aligned with the extraction direction. In order for an interface to be extractable, you need the normals along the interface to point fully in the opposite direction. So notice that this property depends only in the interface geometry, and while keeping the segments fixed, the interface can be actually changed so as to become extractable. In other words, while this example, this part cannot be made extractable no matter what, this one here, because it started from a segment extractable segment, can become extractable or can be made extractable. And what that means is that we can separate the partition into two stages. We first, for every segment on the surface, can find the directions or the best direction along which that segment is extractable. And we then can compute the interfaces, namely partition the interior, into parts which are interface extractable with respect to these particular directions. So in my talk, I'm focusing on this part here. How do we partition the object? Well, the core idea would be, well, first we need to somehow a data to operate on, because a volume is a very general thing. And as we do in geometry processing very often, we discretize it by taking those interior volumes and meshing them in 3D. In this example, this is the 2D, we're generating a triangle mesh. And now we want to look at this mesh and compute a partition of it. How do we go about it? Well, we break our problem into two stages. We first compute a discrete partition where we keep the vertex positions fixed and only label the tetrahedra as associated with one or another part. Note that this can be at best approximately satisfying the interface extractability. As in, without moving our mesh vertices, we might not be able to compute parts whose edges satisfy exactly this requirement of pointing in the opposite direction to the direction along which we want to extract our parts. But once we have those approximately extractable parts, we can now compute an exact solution by optimizing the interface geometry. The details on how we do it are in the paper. In my talk, I want to focus on the discrete step. So the core idea here is, well, this is where we get back to partitioning. And we want to formulate this partition as a constraint labeling problem. Let's look at the constraints and let's look at our criteria. At the core, we want our partition to be conforming. So tetrahedra, which are adjacent to a particular material outer surface, have to be labeled exactly in the same label as the partition, as a segmentation. We want our parts to be manifold and connected. It's kind of a very obvious statement, right? Because we want to be able to fabricate them. And we want them to be optimal, which means we want them to be as assemblable as possible. And we want them to be well-shaped. In particular, we want to avoid redundantly long boundaries or very tiny parts. So let's look at how we formulate this criteria. Well, our core goal is interface extractability, which means this requirement of opposite normal directions. However, as we already noticed, this may not be achievable exactly. However, we can formulate it as a soft constraint, which seeks to partition parts along triangles whose normals satisfy extractability with respect to the two impacted shapes. Notice that even with exactly the same angles, you can have very different parts in terms of how much energy we'll need to spend, how much deformation we'll need to apply to make them extractable. This part would require a very small amount of deformation. In contrast, this one will require quite a lot of deformation so as to become extractable. We therefore bootstrap our optimization by adding soft constraints which prioritize such configurations over the ones here. If we look at the combined energy that we have, which has basically two elements. It has preference for part sizing and interface compactness, which is we want short interfaces. And we have our assemblability keys or assemblability preferences. This can be rewritten in terms of per tetrahedron affinity for a given material and a term for every interface face, which encodes both the preference for compactness and the preference for extractability. This results in a formulation which fits the classical graph cut partitioning framework. And we can use it using the method of Boykov and Kolmogorov, which provide not only an algorithm, but a very efficient software. Once we are done it, well, are we done? Not exactly, sadly, because this method, while it works really well in optimizing the energy function we want, does not guarantee manifoldness or connectedness. Luckily for us, in this particular scenario, enforcing those constraints after the fact is fairly straightforward, and I will refer you to the paper for details. Once we are done with computing the discrete partition, we apply, as I mentioned earlier, an optimization step, which makes our interfaces from approximately extractable to strictly extractable. And this worked quite well. Here is an input. You can try and think in your head how you would partition it. Well, here is our volumetric partition. And here is an actual 3D model fabricated using this partition. Here's another example where we used different materials rather than just colors. What's interesting is while there are other methods which seek to compute partitions which are segmentation aligned and assemblable, all of these methods fail on this particular input. To summarize this element of my talk, we presented here a first robust method for segmentation conforming a assemblable partition, one of whose key elements is this idea of partitioning a discrete domain using a graph cut method. As a food for thought, something which comes up here and will come up in a couple of other examples I'm going to talk about is this fact that the current graph cut frameworks do not support manifoldness or connectedness. Well, from a graphics perspective, these are typically very important requirements. Let me talk about a different problem where partition comes in, and that's hexahedral meshing. What's a hexahedral mesh? Well, you can kind of see it here. It's a mesh of a 3D object whose elements are cuboids. And well, I'm going to say something somewhat controversial. Generating a hex mesh is easy. What does that mean? Well, you can take a tet mesh and split every tet into 4 hexes, and you are done. Except that's not going to give you a useful mesh. What we want is a good hex mesh. And generating a good hex mesh is very hard. A good hex mesh means one whose element shape is close to a cube and whose surface which approximates well the input surface. Good shape meaning as close to a cube, the farther you deviate from a cube, the less useful your mesh is. A good example people say is if I have a single concave element, my entire computation on that hex mesh fails. So what determines quality? Well, if you think about it, if we have no approximation constraints, well, quality is determined by connectivity, which means that a perfect grid is just the best mesh you can get. However, once we have approximation constraints, away from the surface, quality is still essentially defined by connectivity because your approximation constraints no longer apply. Next to the boundary, you really want alignment with that surface to come into place. And what this means, among other things, is if you look at an object, which is a polycube, namely a union of cubes, and the way to formulate it is it's an object whose normals are all axis aligned and whose edges are all straight lines. If you have a polycube, getting a perfect mesh is trivially easy, right? You just break it using horizontal, vertical planes and you get a perfect mesh. So the key idea of polycube-based meshing is, well, if you have an object which is not a polycube, deform it so as to be a polycube, mesh the polycube, getting a perfect mesh, and map it back. The key criterion then becomes, how do we go from an object to a polycube, such that when we go back to the object, we get a quality mesh. And therefore, the question we want to ask is, which polycube? We want the one which is going to give us the best mapping quality. And let's think what mapping quality means. Well, we want to minimize the distortion of the mapping. If you have a high distortion in the map, you're going to have highly distorted cubes when you go from here to here. You also want to have a very small singularity count. The bigger the singularity or corner count, the more distorted your mesh is going to be in the vicinity of those singularities. So, in a way, what we think about polycubing, you really want to think about 3 steps. You have your input model. You want to segment it into charts, which each correspond to a polycube face. You want to compute the polycube given those charts. And finally, and critically, you want to compute a parameterization or a mapping from this polycube back to your object. And in this talk, I'll focus on the first step, the segmentation, because that kind of starts to feel exactly like a classical partition problem. What do we want from this partition? We want low distortion. What kind of proxy can be used? Well, if you think about it, if you look at the normals of the individual triangles on your mesh, the closer the normal is a priori to one of the 6 major axes, the least effort or the least distortion you would need to actually orient them to point towards that axis. That gives you a natural proxy for distortion. We want to minimize the singularity and chart count. A natural proxy for that is the length of the boundaries between your charts. This starts to sound exactly like our classical graph partition. And yes, that's exactly what we can do here. We have 6 labels corresponding to the 6 directions, and we can, for every triangle, assign a cost of how much it costs to orient that triangle towards that label, and how much it costs to have 2 different triangles assigned to different labels. Is this it? Is this going to give us our answer? Sadly, no. This is what we get. And if you look at it, you immediately can see that this is not a valid polycube segmentation. As in, the charts here do not respect the topology of a polycube, and the boundaries between our charts are not really amenable to becoming straight lines. So we have a problem. In particular, we have those turning points, which are places where the boundaries, instead of going in one direction, turn around and go back. And we cannot prevent this, as there is no magic of changing the energy terms in our segmentation, which will help us satisfy the criterion of avoiding such artifacts. However, we can detect them easily once we have a segmentation. Therefore, the approach we took in our work was to use a local search mechanism, which is identifying these problematic situations and correct them by doing a local search within the segmentation space. And again, the details are in the paper. Once we have such a correction step, as shown here, so we go here from an initial to a correct labeling and to a polycube. And here are some hex meshes that we can get. They look pretty good, even for very scary and complicated geometries, and are a huge improvement in terms of quality compared to the state of the art. But in terms of sort of food for thought, the message I would like to take you from this element of my talk is that GraphCut is really a powerful tool. However, classical GraphCut formulation does not support, yet again, the type of constraints we as geometry processing researchers would like to enforce. So there's a very interesting question. Can we generalize the current GraphCut methods to support this type of constraints in some kind of general way, rather than very specifically and tailored to particular problems? Let me talk about one more problem, maybe very briefly, and then we'll see how much time we still have. So, and that's graph partitioning for milling. Yet again, we're looking at graph partition, but for a very different application. So what do we mean when I say milling? Well, for those not familiar with fabrication methods, 3-axis milling is a very widely available methodology for creating 3D shapes in fabrication space. This is a subtractive mechanism. So what you do is you start from a piece of material and you gradually remove material from that piece. And 3-axis mills use a fixed orientation cutter as shown here. So it travels along principal axis and it can mill only along a particular direction. It is a very cheap method because you can literally buy a block of commercially available material and just mill it, being things like wood or stone. And the mills which are out there can operate at a very large range of scales. You can do it at the scale of millimeters, or you can do it at the scale of a house, relatively easily. It's also very precise. However, because your mill has 3-axis constraints, along every given axis, you can only mill along the axis direction, which means you can only mill height-filled surfaces. If you want to mill something which is not a height-filled surface, you either need to split your object into several parts, or you can sometimes mill one surface at a time, then reorient and mill along the other direction. However, in practice, that's really only applicable if you can really flip your object along some very constrained axis. So if you want to fabricate generic geometries, you need parts which are millable, which are assemblable, because once you have parts, you would like to be able to put them back together. So if they're not assemblable, that's not particularly useful. And because you are starting from fixed size blocks of material, your parts have to be small enough to fit into your blocks. In particular, if we look at pre-cut materials, most of them have one direction which is much smaller than the other. We refer to that one as height. And since you are milling a block like this, you really can only in practice mill it along this height axis. You cannot really put a narrow slice of wood vertically to mill it. It's not practical. You need to place it horizontally. So what we need is we need parts which are millable, assemblable, and bounded height. What we also desire is we want the milling and assembly time to be small, and we want to waste as little material as possible. And that's our goal, as we can think about from the perspective of the geometry problem, is to decompose objects into slices which satisfy all the required properties while minimizing time and waste. Now, how do we translate those kind of amorphous criteria of time and waste into geometric properties? Well, they can be translated into our well-known geometric requirements for decomposition. If we have less or fewer slices, and if those slices are inherently bigger, and in particular if they're taller along the milling axis, we are going to require less time, and we are going to have less waste as we manufacture them. So let's look at what we can do in order to achieve those goals of minimizing material waste and time. Well, we can literally, because we have this very narrow slices of material, we can have two approaches. We can mill them from one side only at a time, or we can mill them from one side, then flip them over, and then mill from the exact opposite side. This second setup is what's referred as double height-filled surface milling, where the idea is we mill one side, like shown here, flip it, hold it in place using fixtures, and mill it from the other side. And this is what we are doing in our work. And there are several key observations which enable us to get double height-filled milling. One is that a convex object is a double height-filled for any axis. The second one, which follows from here, is that intersection of a convex shape and a double height-filled surface is by construction, always double height field with respect to the original axis. This follows from the property above. What that means in turn is if we have an object and we partition it into slices such that the outer surface or the exterior surface of every slice is a double height field surface and the partitioning surfaces are cut through planes, then every slice is a double height field surface. And interestingly, because we are using cut-through planes, all our parts are always assemblable. This motivates our approach of using cut-through planes for the composition. So let's look at how we get here. Well, if we have a plate which is already a double height field surface, remember, we still need to cut it because we need to have slices which satisfy our height bound. And what we need to do when we are choosing the cutting planes is to minimize the number of slices and maximize their height, because those are going to improve our time and waste criteria. I'm not going to talk about the details of how we go there, but as we show in the paper, our method is capable of generating less and taller slices than hypothetical alternatives. Now, how do we go from the part of how do we partition specific shapes or DHF shapes? How do we get to partitioning general shapes? One approach could be, well, we're not talking yet about how, is to take the shape and partition it into DHF blocks and then slice every block. The problem is we're going to end up with really small surface regions and therefore very small blocks and many small slices. The observation which enables us to do significantly better is that if we look at shapes like this, so this shape is not a DHF with respect to this axis, but what's interesting about it is for every point on this shape, the occluder of that point is at a distance which is on both sides, is at a distance which is bigger than the maximal size, thickness or height of the slices. Now, what that means that if we are going to now cut this shape using just the height constraint, namely going to cut it using cutting planes, which are at H max or smaller distance apart, the slices we are going to get, independent of where we put the cutting planes, are going to be DHF. And that's very interesting because it means that if we can identify blocks like this, or segment our objects into blocks of this shape, which satisfies this criteria, then just our baseline slicing algorithm is going to produce DHF slices. So, and the LDHF regions, or blocks which satisfy this relaxed constraint, are naturally much bigger than the blocks which satisfy the more-narrow DHF constraint. So getting these blocks, which are much bigger, we're going to end up with a lot less slices, promoting our requirements of less time and waste. So in a way, if we think about algorithm, we have two steps. We first compute blocks which are LDHF, and then we slice every one of those blocks, which allows us for a lower slice count and taller slices than alternatives. The way we compute those blocks is we're looking for blocks, remember, whose surface satisfies this LDHF constraint and which are bound by interior surfaces formed by cutting planes. And we do it using standard BSP iterations where we separate one block at a time. The challenge is, how do we find the block whose separation is predicted to lead to the best decomposition overall, rather than necessarily the biggest block? And the idea here is that we're going to be looking for blocks which are bounded by LDHF surfaces and planes which are orthogonal to the surface axis. Why orthogonal? I'll refer you to the paper. So we are going to be looking for regions like the green ones here, which are continuous, which are bounded by axis orthogonal planes and LDHF surface regions. The question is, how do we find the best such region to separate? If we do it greedily, namely by saying, hey, let's find the biggest region, we're going, as very often is the case with greedy, to end up with suboptimal results downstream. So what we are looking for is to select the best strip. The way we do it is by computing our possible ones and then computing the best by balancing the quality of the blocks that corresponds to that strip against the quality of the decomposition of the remainder. And this is where you can start thinking about where our partition algorithm comes in. So what we are looking for is to predict a volumetric partition, but we do it using a surface segmentation. What do we want from the segmentation? We want to minimize the number of blocks in the output, and we want to have our charts and our segmentation to overlap our LDHF strips with respect to those milling directions, and we want to prioritize directions that facilitate milling less accessible triangles, namely triangles that cannot be milled from other directions. This gives us, again, our friend the graph partition, where our compactness term is very straightforward. All we want to do is to minimize the length of the boundaries between our charts. In contrast, the most of our smarts, or most of the energy spent in how to properly compute the desired parts, goes into the costs per triangle, which account both for how accessible that triangle is with respect to each direction and into how good that direction is in general. Notice that here we have a label for every milling direction. So we operate in a discrete space with very many labels. However, our graph partition, in a sense, acts as a label selection mechanism, where out of a set of, say, dozens of directions, we're effectively selecting only a few, which we then in turn are going to be used to compute our blocks. Once we have done with that, we can complete our fabrication pipeline and generate actual, let's say in our case, wooden parts and assemble them together to generate our 3D models. And as we show in the paper, our method reduces waste and milling time by 43% compared to existing alternatives. From the perspective of kind of summarizing this approach, what it enables is a new computational milling pipeline using pre-cut materials. In the technical interesting bits here are this use of DHF decomposition and the slicing method, which I didn't have time to talk about today. From the perspective of partition, I think the interesting element here is the fact that we are using graph cut as an approximation of the coverage problem, namely as one of locating the best labels to use rather than just the boundaries between the existing labels. And lastly, just before we wrap up, I wanted to very quickly talk about a very different graph partition problem, which arises in other geometry settings. In this case, it comes from the problem of computing descriptive curve networks from 3D models. Such networks can be used both to encode our objects visually and to reconstruct the input geometries algorithmically. If I look at the construction of those models, it's something which for humans is very natural, but the question is, how do we do it algorithmically? And what we are looking for is for curved networks, which are descriptive, namely viewers can visualize the model from a 2D projection. What that means is that in turns that can be broken into two parts. First, we want to be able to visualize the 3D curves from that 2D projection, and we want to visualize the 3D surface from the curved network. We want, lastly, we want this network to be very compact. We don't want a lot of curves. And in the paper, we discuss in details what criteria there are for the curves to satisfy our criteria, our requirements. And we show that the projectability is best achieved by curves which are planar and orthogonal. If you think about psychodescriptiveness, that's a question of how do we go from a curve in 3D, which in this case you can imagine what that curve is, to the 3D surface. Is this a surface you imagined? Probably not. However, given this network, this is probably a surface you imagine. And research and observations of artist drawings suggest that human observers perceive drawn curves as curvature lines and predict the interior of the surface by imagining the interior curvature lines as smoothly interpolating the surrounding curves. In other words, when artists draw, in addition to coarse and sharp features, they draw what's known as dominant flow lines, which are curves which are aligned with principal curvatures and are smoothly extended across anisotropic areas. Those curves are dominant if they delineate large areas of smoothly changing curvature. So how do we go algorithmically about achieving this effect? Well, if you want to think about it, you can think about first computing a dense set of flow lines and then sparsify it to select the dominant ones. And those flow lines should naturally be aligned with curvature. However, directly tracing flow lines is non-trivial because we don't know when to finish, there's a drift effect, and there's a challenge in propagation across anisotropic areas. So the core idea behind our work is, well, let's start with a curvature-aligned mesh and then compute flow lines as sequences of mesh edges on that mesh. However, if we do it naively, starting from this way, if we look at the paths that we trace, we can try and think about the fact that we may want to trace paths which are as straight as possible. This works here, here, but it doesn't work here. The challenge is that local tracing does not work. However, if we think about the mesh in general, we may notice that dominant flow directions correspond not to a single traced curve, but to groups of long, similarly directed edge sequences or strands. And we can try and think about how do we get those strands. The idea is we want to trace them jointly. Rather than extract them one at a time, we want to group edges into groups which naturally define strands. So we don't know, however, the number of strands a priori. We do know that given an edge, we want edges which are either consecutive to it and almost have the same direction, or parallel to it and have same direction to be in the same strand. And we know that edges which are perpendicular to our edge or near perpendicular do not want to be or should not be in the same strand. We can think about assigning positive weights to the first group and negative weights to the second. And we want to have a partition method which accounts for those weights. As it turns out, this gives us another variant of the partitioning problem, what's known as correlation clustering. Correlation clustering maximizes the following function, where Yij is an indicator function. It is 1 if the entities, so the edges in our case, I and j, are in the same cluster, and it's 0 otherwise. And correlation clustering is amenable to this processing of both positive and negative weights, as in our case. It is yet again NP-hard, but an efficient solver exists. So we can use this approach to obtain strands. From there, we can go to flow lines, get our dominant flow lines, optimize them, and get some very nice models. And I think to summarize, flow rep gives us a very nice formulation of computing this type of curved networks out of 3D objects. And for me, one of the most interesting things actually about this paper was this use of correlation clustering as a means of grouping. I have since used it for a couple of other settings. I'm going to skip those because we are running out of time. I will refer you to the details in the paper, in the relevant papers, and I'll just try and click here and go further down in the presentation, if it lets me. And so this is another paper where we have again used correlation clustering, and it seems to be a very efficient mechanism for a lot of geometry problems where we really do not know the number of clusters a priori, but have strong positive and negative grouping cues. To summarize, partition has many uses. It is also sadly NP-hard. However, there are many existing methods which are effective for some problems. The question for me comes up in two interesting spaces. Are there more applications where we can use different flavors of partition? If I think about it, the famous "I have a hammer, give me a nail" example. And the question is, can we develop effective solution for other or harder variants of partition? Thank you for your attention.
Okay, thank you, Professor Sheffer, for giving such a great talk. And personally, I really like the analogy between the nails and the hammers. So I think we will all seeking for better applications of such a great technique. And yeah, and so as usual, we'll have the joint Q&A session since we only have 5 minutes left. So we probably will just have a short one. And I will ask the questions interchangeably. So the first question for ask you is because you mentioned the specific representation can result to say this efficient algorithm. Is there any theoretical side to this claim? Did you compare to with other algorithms, and also why that's the case?
No, I didn't understand the question. Is this about a specific problem, or is this in general about graph partition?
Oh, wait, sorry, Professor Sheffer, it's a question for the opener, ask you.
Oh,
yeah, but.
Sorry, I didn't understand it there. Can you repeat that? Is there a theoretical comparison with the algorithm? Is that?
Yeah, well, just wonder why you say it's efficient.
Oh, because yeah, the other algorithms for tilings, they are based on the explicit graph relations and the symmetry relations. So you need to the translation part is very, very computationally efficient because you can make the copies very fast, and the hashing to compute the edges also helps you a lot. So you don't need the common meshing, or neither the graph, the complete graph representation of the mesh, which grows very large with big tilings. So this is why.
Oh, okay, that makes a lot of sense. And another question for Professor Sheffer is we wonder, as you mentioned, for assembly, why is it important, say, to have this manifoldness? Because the way we were thinking about it is in the real world, we can still 3D print a tat mesh with a non-manifold vertex. So why this is important?
It's extremely fragile, right? I mean, if you have a non-manifold vertex, it means you have an object whose thickness goes to 0 at a specific vertex or at a specific edge. Mm-hmm. So if you have a thickness of 0, your object becomes extremely fragile. So you really don't want it in real life.
I see. But can you still say assemble in the same way as you assemble, say different parts? You don't really glue those together, so it's not fragile anymore.
Well, you can separate it into multiple parts, yes. But that kind of defeats the purpose of, you usually want less parts. The less parts you have, the less material you waste, and the less assembly time.
Oh, okay.
Yeah.
I see, it makes a lot of sense. And also, another question for ask you is we wonder what will be other possible applications for such a representation based on complex number beyond just say do theoretical telling.
Sorry, can you repeat, please?
Oh yeah, we just wonder is there any other applications for such a representation based on complex number except for theoretical tellings?
So we have seen there are some works doing this with quasi-symmetric or quasi-periodic tilings also, but it's scattered. So, and we're trying to bring some applications also.
Okay, cool. Looking forward to seeing those. Okay, another question for Professor Sheffer is could you clarify the definition of millable accounts for does it account for the resolution of the end mill?
Excellent question. Yes, if in real life you want to account for the resolution of the end mill, and what that means is two things. A, there's a question of just the level of detail you can mill. B, the precision you really want. Like in practice, you actually, in a way, that means that you can relax somewhat your height field constraint because you are not, because your precision is bounded by the precision of the mill. So you can actually consider things as millable if you have very small regions where you won't be able to mill them anyway. Like you can think about the resolution of the mill as, in a way, it relaxes your height field requirements on the one side. At the same time, yes, you might be unable to mill very narrow regions if they're narrow with respect to that particular axis. And in that case, you might want to mill them from another direction. That's where this criterion of accessibility comes in, where we're trying to mill triangles from the direction along which they're most accessible.
I see, I see. This is reasonable. And thank you for clarifying this. And also, like, we wonder, like, can this, like flow lines, like as you mentioned in the last paper, like used to visualize the curvature directions in a surface, like, for example, the root lines of a developable surface?
Yes, but the question is, so the interesting things about flow lines are twofold. A, where do you trace them and how on isotropic areas? Because obviously then you don't have clear principal curvature directions, right? And the second one is, we know that from a human perspective, if you think about 2D projectivity, you want planarity. Now, curvature lines, exact curvature lines, are not necessarily planar. So there is a bit of an interplay there between how much you want to be strictly aligned with curvature versus how much you want to prioritize planarity. So there's an interesting kind of balance.
Oh, okay. Okay, cool, cool. I think that's a cool aspect to think of this. Okay, and one last question is, like, for the surface to volume segmentation problem, what will be the most advantage of using discrete optimization than using, say, for example, implicit function optimization?
Good question. I think part of the answer is, as I quoted before, I have a hammer, give me a nail. I know how to do it with a discrete set. Okay. I think with implicits, it might be possible. I don't know how. So if somebody wants to try and do it with implicits, I'll be very, happy to talk with them.
Okay, cool, cool. That's like a future direction. Okay, so I think these are like our questions for now. And if like anyone have any other questions, just feel free to post it on our Discord channel. And yeah, so we will thank like our speakers for today, and also thank the artists to design like this session's poster. And also as like a little heads up, like we are gonna take a 2-week break, like as the next step, because there will be like the SIGGRAPH rebuttal and also SCCV deadline. And we will be back at March 24th. And yeah, see you